Welcome everybody to week 7, day 2. We are having a live recording today and Monday, and then on Wednesday and Friday of next week it'll be a pre-recorded session. I think. I'm still figuring that out. But as for now, it'll be live today and Monday, and then pre-recorded on Wednesday and Friday. Alright, so we got a lot of things to talk about today. First is we're going to go over linked list one more time. The competency exam for linked list is coming up, so we're going to go over it one more time and maybe give you a new perspective on how to think about code. So one of the reasons why we do object-oriented programming and make classes and do ADTs with like private member variables and a public interface is to preserve invariants. Invariants are things that must always be true on your class. So for example, for a linked list, you might have an invariant saying the size always accurately contains the size of the list. And so if you call any non-const method, because a const method can't change a class, right? Like if you call get size, like it can't change the class because you've marked it as const. For any non-const method on your class, you have to look at it real carefully and see if your code could break one of the invariants somehow. And you have to, and that's kind of the most important thing, maybe even in this entire class, which is thinking about what things you want to guarantee to always be true in an object, and really, look at things and make sure that you're handling them properly. For example, if you have a pop function or a delete function from your linked list class, and your delete function doesn't have size minus minus anywhere in it, your code's wrong, because it's not going to be maintaining that invariant for the size. Or if your code nowhere within it ever says head equals null or tail equals null in your delete function, your code's wrong. I guarantee you your code's wrong. Because at some point, if you keep deleting from a linked list, it will become an empty list, and then you need to set head and tail to null. So if I look at your code, and nowhere within there do I ever see the line head equals null, or head equals null pointer, or head equals 0, or tail equals 0, or tail equals null, or tail equals null pointer. If there's nothing like that anywhere within your delete function, it's wrong. And I was telling Mincarelli about this in the previous section, which is that one of the ways that I actually got really good at programming was through TAing, through doing what he does. And students would come to me. I taught this class over and over. And students would come to me with help on linked list assignments. And I could sort of like defocus my eyes and just kind of like look at it from a big picture standpoint and be like, no, your code's wrong. Your code's wrong. And I could do that because I would think of code in terms of invariants. And I think about things that have to be, the invariants that have to be maintained. And if I'm looking at your delete function and nowhere within there do I see the line head equals null, I know your code's wrong, because it has to be in there somewhere. So I have a little PowerPoint presentation here on invariants, and we're going to go through some actual student code and see if this thing loads. There we go. All right. And I'm gonna kind of give you my philosophy on invariants and how to like look at code and how to write code that doesn't have bugs in it, so to speak. It's really important, this lecture today, because in the future, you're going to become a professional programmer, presumably. Even if you don't, you maybe just work incidentally in it. Every time you do something, every time you change something, like there should always be that nagging like question mark in the back of your head, like, did I forget to do something? Did I break something? Did I violate an invariant somewhere? And you're not going to have that nice testing functionality that I gave you, where I test your linked list node class and linked list class extensively. You're not going to have that, and so you have to do it yourself. And that's something that a lot of students in this class struggle with. It's like, my code's wrong and I don't know why. Professor, tell me why my code's wrong. And a lot of times I want you to develop that skill of like trying to figure out where your code is wrong and testing your own code. Like a lot of students only run my input test run, and that's bad, right? Like you should be running tests on your own code and running your program and putting input into it and seeing if it works and things like that. And so while the input tester and the class testers and things like that I make for you are really good and helpful. At the same time, like, they can turn into a crutch if you don't know how to test your own stuff, so that's kind of what our lecture is on today. Not on testing so much, but like how to think about your code, like what to think about when you're coding. So whenever you do a push or a pop or a delete or whatever, there's always going to be like some core functionality that needs to be taken care of, right? Like if you do a push function, you're going to be calling new, right, on a linked list. Somewhere within there's going to be a new where memory is being allocated. That's what I color code as, like this yellow, orange, gold color. That's the core functionality. But every time you change a linked list, you also have to think about your invariants and see, am I breaking the invariants somehow? And you just every time you do something, you have to just go through all the invariants in your head and just be like, am I breaking this one? Am I breaking this one? Am I breaking this one? And for the linked list class for EU4, there's basically 3 invariants. The first one is list size must always have an accurate count. And a lot of people's code I was looking at over the last week, they just weren't updating size properly. They were doing it in some places, they weren't doing it in others. And so if you increment size when you push, but you don't decrement size when you pop, then it's good. Like, and you use it to like see if a list is empty or something. Like it's game over. It's just not going to work right. You have to, see out all the things helps, but also, I think a skill that I really want all of you to develop is just testing your own code, like making test cases for your own code, just running your code by hand and just seeing if it works. Like build a linked list, call push front a bunch of times and print it out and just see if it works. So there are 3 invariants for the linked list class in EU4. First is you have a size variable that always has an accurate count of the size. Second is head pointer must always point at the first element in the list, unless the list is empty, in which case it must be pointing at null. It must hold 0 or null pointer. And then ditto for the tail. So the tail must always be pointing at the last element of the list, and if the list is empty, then it points to null as well. And I've color coded this for these slides. I've got a color coding scheme where I've got the functionalities in orange, we've got the size invariant in green, the head invariant in red, and the tail invariant in blue. And I'm about to show you some student code, and I want you to look at it and see if the student is actually maintaining all the invariants as he should be. Okay? Because every time you change your linked list, you have to look at all 3 of them and be like, did I do that? Did I do that? Did I do that? And it just needs to become a habit for you. So here is my code, and you can see my code for push. This is a singly linked list. I'm pushing at the front at the head. I'm adding a new node above the head and linking it up and moving head up. So this is going to new. So you see it's a push. I do have a new in there. So functionality check. It's, you push 50. It's going to save 50 in the data payload of the linked list. And its next pointer is going to be set to head pointer. Now, if head pointer is null, its next will be null. That's fine. That's not a dereferencing of a null pointer. That's actually fine. You don't actually have to check for head being null there. It works fine. We then move head to be the new pointer. If the list size was 0, then we update tail pointer. The only time push will ever change the tail pointer is if the list was empty before. And so if list size is 0, tail pointer equals head pointer, which is another way of saying the new pointer. And then we increment size. And so you can see my code, functionality, head invariant, tail invariant, size invariant, check, 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 done. And a lot of times when you write good code for linked lists, it's actually small, concise, and readable. You just have to make sure that you're checking the boxes. All 3 of the invariants are being updated. If you forget any of these things, your code's wrong and will break. And that's the problem that a lot of students were having on this assignment, which was that they would forget just one thing. Like they would move the head pointer down, but they wouldn't set, like when they popped off the front, they'd move the head pointer down, but they would not set the previous pointer on head to null. And so the code would break. If you forget even one thing on a linked list, it's going to break. You have to be perfect to do linked lists properly. So, and that's a problem. Everything works except one thing, and it's rough. So, this is my code. Let's look at a student's code. So here is their push class, push function rather, push method. So they pass it 50, and they say if head pointer is null and tail pointer is null. So they're checking for an empty list. I did it with list size. They're doing it by checking to see if both the head and the tail pointer are null, which is a bit, it's fine. It's a little bit more verbose than I think it needs to be. You could just say if not head pointer, because head pointer is null whenever tail pointer is null. So you don't technically need to check for both, but whatever, it's fine. It's technically correct, I guess, even though I wouldn't do it that way. So take a look at the code, and just I'm just gonna shut up. I'll even pause the recording, and I'll give you all like I'll give you like several minutes actually to like look at this code, and if you see anything wrong with it, and I'll let you know there's problems with it, post it in chat, and then I'll unpause the recording in a couple minutes, and we'll talk about it. Okay. And if you're watching this as a recording, just pause the recording now and just stare at this code and see if you can figure out what is wrong with it. Okay, I'm gonna pause now. All right, so set next at new node. That technically will compile. Head pointer is a pointer to a node. This is making a variable of type node and taking a pointer to it. The trouble here is that they're not actually newing any memory, right? This new command here is actually really important because it actually allocates memory off the heap, not off the stack. And that memory is permanently allocated until you call delete on it. This code here, even though the name of it is new node, it is not actually newing a node. That actually got me when I looked at it. I'm like, oh, okay, wait, no, there's an underscore there. Wait a second. Yeah, this is a stack allocated variable. This is a regular variable. And when do regular variables go away? Anyone know? Yeah, this is a single linked list. When you exit the scope, yeah. So this variable here is being deallocated right here. But his list is maintaining a pointer to it. This is a huge no-no. You almost pretty much never, ever want to take a pointer to a stack allocated variable. And if you do, like, you just use it immediately and then like don't use it again. He's actually saving the memory address of a variable that has been deallocated. And the scary thing is, like, his code actually worked some of the time. Because head and tail were pointing at whatever chunk of memory this was, and the data was still there until it wasn't, until it was reused. So this code almost kind of worked. It compiled, and he's like, well, if it compiles, it must be correct, right? Nowadays, a lot of compilers will throw a warning saying, watch out, you're keeping a pointer to a stack allocated variable. And if you ever see that warning, just be like, no, don't do that. I did that once accidentally in a program of mine where I somehow preserved a pointer to a stack allocated variable after the thing had returned. And that was hours of my life trying to track down that bug. Sporadic crashes and things like that. It was just like, what? Horrible bug. So yeah, technically they're updating the head pointer and they're updating the tail pointer. Okay. They're doing the functionality. If they fix this, then, if they fix this to be a new, and then you don't need the ampersands anymore, it would be a node pointer, right? It's supposed to look like this: node pointer equals new node. So this would new the memory, and then you set head and tail, and that would, you can clean that up pretty easily, and the size is good. In fact, he got the size in both branches, so the size invariant is being maintained. Good job. Over here, yeah, the tail pointer is missing. But I think it's okay, because the only time the tail pointer changes when you push onto a list is when the list is empty. So if you had nobody on the list and you push 50, then head and tail are going to point at the new guy. After that, only head changes. So actually, if we're looking at the color coding, okay, okay. One trouble: this thing here for the head pointer is not actually setting the head pointer. So this is actually setting head pointers next. So the pointer that head is pointing to is the new guy. we're not actually moving head like we should. So what's happening here is that he's creating a new node and saving 15 to it or whatever, and it's setting its next to heads next, and then it's setting heads next to it. So it's actually inserting in the second spot in the list. It's not actually inserting at the beginning, it's inserting one after the head. So head never changes, and it's always inserting after head into the list. So this is what I was talking about. Like, you know, you sort of defocus your eyes, you look at it, and you start off, you're like, okay, they got all the invariants here, but look, there's no equal sign here. There's no head equals something, so the invariant is not being maintained. It's setting head's next pointer, sure, but nowhere in here does it actually say head pointer equals something. So that's wrong. That's wrong. And then, like I said, we don't need the tail pointer. So let's go on to a harder one. All right, so again, the gold color is the core functionality, and we have blue for the tail invariant, red for the head invariant, and green for the list invariant. Defocus your eyes, zoom out. Which invariant are we absolutely guaranteedly not maintaining here? Right. I'll pause it and give you guys minutes to read through this code because it's interesting. But you just kind of zoom out a little bit and you just look at it and you're like, what color is missing? There's like a yellow, orange, whatever you want to call it. Red. Yeah, we're missing red. Nowhere within this code do we see head pointer equals something. This code is guaranteed wrong. And this is a talent that I developed when I was in Mincorelli's shoes. I would just look at code and you go, nope, your code's wrong. And they're like, how could you know that? You haven't really gone through it. I'm like, nowhere within this pop do you ever say head equals anything. So you are not maintaining the head invariant. Remember, head pointer must always be pointing to the first node, and if the list is empty, it must be null. And so if you have a list size 1 and you pop the last element off, you must set head to null in there. So I would just look at this and be like, it's wrong. It's not going to work when you pop the last element off, guaranteed. And they're like, wow, how do you do that? And I'm like, because you just start thinking at like a higher level, right? You like kind of zoom out a little bit. You're like, all right, they got the list size, that's being maintained. I see on their tail pointer, we're going to have to go through that and see if that's correct, but they're doing the tail pointer invariant, they're doing the size, they got a bunch of functionality, which we're going to have to go through and figure out. But the head, missing. They are nowhere within here setting the head pointer. This code is guaranteed wrong. And it will be wrong when you pop the last element off the list. And you sort of start feeling like a Jedi when you do that, because there's a lot of stuff going on here. Like there's a lot of stuff going on, and there's a lot of errors in this code. But yeah, you just look at it and you're like, nope, wrong. So petition to your homework assignments all together. So when students make a mistake, we can take several minutes to look at the code, see what's wrong, come up with a useful solution. That could be fun. Maybe the next one I'll let you do mob programming or something. Just let everybody vote on the bugs, or I don't know, something like that. That could be fun. Okay, so I'm now going to pause the code. So this is so what we were doing for their assignment is push always comes at the head, pop always comes off the tail. Okay, so there's no insert at beginning, insert at end. It's just push is always at the head, pop's always popping off the tail. I'm going to go ahead and pause the stream again for several minutes, and I want you to like really go through this and see if you can spot how many errors there are in this code and what is going to happen when this code runs. Okay? If you have to like sketch out an example linked list, 3 or 4 elements in it, and really run through it. I'm going to give you guys 4 minutes to look at this code. Okay? And just any observations you make, just post on chat channel. And again, if you're watching the stream at home, just go ahead and pause and really go through this. This is actual student homework that, you know, I didn't contrive this example at all. Okay, pausing now. And we're back. So, a lot going on here. First of all, again, he's checking to see if both head and tail are null. You can do it that way. I would just say if the size is 0 or if head is null. You don't need to check both. Return false. I don't know what's going on with that. It will return 0, I guess. But Just return 0. Yeah, like why false? I don't know. It's an int, and that's a Boolean. Technically, it'll work, but you probably shouldn't do that. Int data equals till. This should be one line. Like you should go into Vim, hit Shift J. Do you know Shift J? Join 2 lines, and so that'll put this line up here, and then delete the extra semicolon in the data, and just say int data equals tail pointer points to get data. A lot of people write code like this where they declare a variable and then they initialize it. I don't like that. I don't ever like seeing uninitialized data, uninitialized variables. If you don't need the variable yet, don't declare it yet. You know what I mean? So, okay. Node pointer cursor. So this is like a temp pointer. Cursor equals head, and then we have this fantastic for loop here. For int I equals 0, I is less than or equal to list size -1 I plus plus. So I need to draw. I believe in Ray. Yeah. I don't. It's because back in the day, like in the old SeaWorld days, you had to declare all your variables at the top. Like you would have to be like. You'd have to go like int x, y, z, and then like you had to declare all of your variables at the top of the function and then use them down below. And that hasn't been a requirement in C for a long time, but still some people write code that way. All right, so let's sketch out some lengthy listies. So let's see, we got 10, which points at 20, which points at 30, which points at 40, and we got head is here, and we got tail is here. Okay. Whenever you work with invariants, you should always assume that the invariants are preserved before the function call, right? And size would be equal to 4. So he's making a cursor, which I call a temp pointer, and then he is going to have this for loop here run. The size of the list is 4, so it's going to run from I equals 0 to I is less than or equal to 3, so it's going to run 4 times. And this is another reason why you should always follow the pattern for the for loops, so you know how many times your code's going to run. So for int I equals 0, I is less than or equal to 3 is actually 4 times the code's going to run, and so 4 times it's going to say cursor equals cursor points to next. So let's go back into OneNote. So this is going to move the cursor to the next 4 times. So cursor is going to go, bloop. It's going to go 1, 2, 3, and 4. It's going to actually be pointing at null because the last element of tail is pointing at null. Cursor is now pointing at null. This is a order n method of saying cursor equals null. Okay, so cursor's null. We then create another temporary pointer. So we got one temporary pointer here, we got one temporary pointer here. This temporary pointer is equal to tail pointer. So we got cursor pointing at null, and then we're making a temp, and the temp is pointing at tail. Okay, then so temp equals tail, then tail equals cursor. So tail is now pointing at null also. So cursor is pointing at null, tail is pointing at null, temp is pointing at the artist formerly known as tail, and then we set temp equal to null. So I don't know why we just set temp equal to tail, because temp is now being set equal to null also. So now we have cursor pointing at null, tail is pointing at null, temp is pointing at null. We then delete null, which doesn't do anything, by the way. It's not a seg call. It's well-defined behavior. If you pass null to delete, it just doesn't do anything. Okay. So you are more than welcome to delete a null pointer. It doesn't do anything. It just returns. So this does nothing. And the important thing is it's not deleting this. Like we thought it would be deleting the last element of the list. We thought it should be deleting this person here. but it's not. So if we remove like that line, then at least the functionality is correct, right? Then at least we're deallocating the last element of the linked list. But because for some reason he decided to just set it to null, I don't know. We have 3 null pointers at this point. It wouldn't set 40 to null? No. Now, if you say temp equals null, temp is just a pointer. It's just a memory address. And so temp is an integer. And so the integer stored in temp at this point is 0. It doesn't do anything to this. If we took that out, at least it would deallocate the memory. And then tail pointer set next null. So what he's trying to do here is set. I think he expected tail to be pointing at this one, and then setting 30s next to be null. But instead, tail is null because the for loop's wrong. And so this right here is your good old classic null pointer deref. You can never have code that looks like this. Null points to anything. This is an explosion. Okay. If null points to anything, you're dereferencing a null pointer. Okay. That's an explosion. And so his code only segfaults because his for loop's wrong. Like if he had changed this -1 to a -3, I wouldn't write code this way, but at least it would have been correct. He was off by 2, actually. It was an off by 2 error, which, yeah. So if that was a -3, then this would probably mostly work, I guess. It would delete the old tail. It would move tail up a level. Tail's next to be null. Yeah. And so if we fix that and we fix this here, the code's mostly correct, but we're still forgetting one invariant, right? Should there be a get previous? There isn't. This is a singly linked list. This is a SL list. Singly linked list. So there's no prev. And so whenever you have a singly linked list, if you want to pop off the tail, you have to write a for loop like this, where you go down the linked list and find the previous. And this is of course, order n operation here. So that's why we like doubly linked lists. Okay, singly linked lists suck. I basically just never use them. They're just terrible. Yeah, like I said, when Chris Glaves did a faculty peer evaluation for me the other day, he's like, it would have been nice if you could have given some examples of when you use a singly linked list, and I was just like, I don't. I really don't. I'm sure there's some people out there that it's their favorite data structure, and I'm insulting them and their family and their dog, but yeah, just no. In the standard library, they're called forward lists. If I have to use a linked list, I will use list. I never use forward list. If I'm making a homework assignment and I want you to get practice with it, sure. But unironically, I don't think I've ever used a forward list. They're just terrible. Okay. So size is being updated. So the invariant you all said earlier, the invariant that is not being updated properly is head. And so we need to do something in here with head. And that thing is right here, which is to say if the new size is 0, then head equals tail equals null, right? Or null pointer, or 0, either way. Null pointer, either way. Either of the 3 options will work. Null pointer is the preferred way of doing it. Okay. So, yeah. Did you guys have fun with that code? Give you a headache? What do you think? It is actually valuable looking at other people's code sometimes and trying to decipher it and debug it and get into it. Large amount of yellow font. Yeah, just another learning experience, yeah. If you want to get good at coding, there's kind of two opportunities you might want to look into. The first is becoming a Min Corelli or Betancourt. The tutorial center is always looking for computer science TAs because we, as I'm sure you're aware, like, a lot of these assignments can be hard, and if you get a bug, you need help. If you get stuck, a lot of times you need somebody else's help to get unstuck, and that's one of the reasons why I tell you all, like, don't wait till the last minute. There were 10 people on the server last night at midnight, which is, I guess, better than most. How'd you change to do this? Use of ampersand? No, you're rarely going to see the use of an ampersand in there. Yeah, you just call delete on the old tail, and then you move tail up to the previous, and set tails next to be null. So all the big pieces are in here. The only thing they forgot is, like, when you pop the last element of a list, that invariant kicks in. If the list is empty, head has to be null, tail has to be null. You forgot about that. And like I said, there is zero room for margin of error in a linked list. If you forget anything, your code's going to segfault or crash or infinite loop or something. The good news is most of the code is actually not bad, right? When you reach a certain level of competency, like, most of these linked list things are actually quite short to write. Newer programmers actually write a lot more code than is needed. A lot more code than is needed. Okay, so my pop function for this would be something like, if the list size is 0, return 0, not false. If the list size is 1, head equals tail equals null pointer, and then I would do something like this. Like, I would save the value in the last element, set head and tail in size all to 0 to null, then return that value. And then otherwise, I would basically do what he had there. Like, if it's a single linked list, you have to loop down to one above the tail, delete the tail, move the tail up, set the new tails next to be null. All day. Okay, so other than becoming a Min Corelli, there is, I posted a link earlier, you might have seen it during the previous class. We were kind of messing around on HackerRank earlier today. This is another way of getting, like, a lot of just practice in. One of the issues I have with the Zybooks for data structures is they don't actually have programming assignments, which are coming, apparently. I've been asking for it for like 5 years, but get interview ready for top companies. Cool. Go away. But they're still not out yet. Maybe this summer. Maybe if you fail the class and retake it, you'll have Zybooks programming assignments. But until that happens, I would recommend you go onto websites like HackerRank, LeetCode, Code Wars, maybe Code Academy. It's kind of basic. And the reason why I recommend that is because it gives you an opportunity to get your practice in. Programming is like learning a foreign language, and there's just no shortcut to getting good at it. Almost all of the students that struggle, not all, but a lot of them, they're either not directing their time productively, like they'll just sit there randomly changing things in their code until it works, which is a horrible way of learning, or they're not putting in the time, right? If you click through the Zybooks without reading it, when it comes time to write a program using a linked list, like, it's going to be a lot harder for you, because if you don't have a conceptual understanding of linked lists, you will not be able to write code for a linked list. But so a question I get a lot is like, where can I practice more? Where can I get my hours of practice in? It's like with Japanese. I've got an app on my phone here called Satori Reader, and here we go, Satori Reader. And so if I want, I can practice my Japanese, like on these plane flights that I was on. I just click on this and pull up a story, and you can see it's got Japanese on here. And if I click on a word in Japanese, it defines it for me. And so I can just sit there and just very slowly go through it. And if I don't know a word, which is often, then I click on it and it tells me. And if I want, I can add it to my study list and then do flashcards and things like that. But it's just an opportunity for me to keep grinding and keep putting the hours in and keep just working on it. And I don't even know why, because Japanese is so hard. It's such a difficult language. But it's just kind of my personality. Like when I start something, like I hate being terrible at things. And so pre-pandemic, I went to Japan every other year over the summer, and I just got tired of being incompetent. And so like I've taken a year of Japanese now, and I've got a Japanese tutor now, and like I said, I'm like doing these like readers, and I do flashcards all the time and things like that, just trying to grind. And you have to have that mindset for programming as well. So same as the worst. Yeah, it's such a hard language. It's really ridiculous. Tell us to always initialize your variables in Japanese. I wish I could say that. But you have to have that same mindset for computer science. It's not something you can kind of like put in like 50% effort and be like, C's get degrees, and like just kind of, this one looks hard, I'm not going to do it. Like it's going to be a train wreck if you do that. You need to put in the time, you need to put in the effort. It's like learning a foreign language, you just have to keep practicing. And so the good news is for websites like HackerRank, they actually have like an entire section just for linked lists. So if you register on it, here, I'll post the link here. Sigma, any apps you'd recommend for Japanese or for C++? Satori Reader is actually really good, but you have to have about probably a year and a half under your belt, or you're just going to be flopping. What I recommend is actually this, or I'll post some other links on there as well. So like if we click on, if you register on HackerRank, you go down here and go to data structures. These are all things that you're going to be learning in this class mostly. You can sort it based on difficulty, and you can sort it based on topic. So if we go over to linked lists, you can see I've solved quite a few elements of linked lists. For example, printing all the elements of the linked list. Oh, look at that theme. Look at that theme. Dark theme. Thank you. Okay. So if you wanted to start just practicing linked lists, I would go to HackerRank, click on the linked list, and just start from the top and work your way to the bottom. And so this code here, they've done main for you. You can ignore all that. Just leave it minimized. And you have to write a function called print linked list. So you're given a pointer to the top of a linked list, and you have to print all the elements in it. So it has a little reference here showing you what the class kind of looks like. It's kind of wrong. It actually has a constructor, and the constructor only takes the data. It's so frustrating. Like you can't pass in two parameters to the constructor. It's so stupid. It's about drive. It's about power. We stay hungry. We devour. Put in the work in the hours. Take what's ours. It's funny. Let's talk about being bad at things. Yeah, it is very frustrating. And so, like I've put in like a year, going on a year and a half of Japanese now, and I still can't have even the smallest conversation with somebody. It's super frustrating. But just keep on that grind. So how do we do this? Anyone want to? Kearney speaks good Japanese. Nihongo ga heta desu. Watashi no Nihongo ga heta desu. My Japanese is garbage. So yare. So who wants to take a crack at this? This is a classic linked list traversal algorithm. How many people here remember the algorithm for traversing a linked list? While you're doing that, I'm going to show you some things I like to do on this website, which is I don't like their class names. They're too long. And so I do things like this using linked list equals singly linked list. Singly linked list node, like that. And then I can come in here and why is this not in Vim mode? What did I ever do to you? Vim mode. Thank you. C++ 20. Ooh. I don't have starter code for that one. Okay, let's go back to 14. Undo. Okay. All right. So using linked list equals singly linked list node, and then I can just. I don't like really verbose names, but this is just my own personal predilection. So we got a pointer to the head of a linked list. We're going to print out all the elements. For list, yes, very good. So classic list traversal algorithm for linked list. Pointer temp equals head. As long as temp is not null, temp equals temp points to next. That's our classic traversal algorithm, and we're just going to see out temp points to data with a new line, and we will need to be using namespace std as well. Okay, so that is that. Run it. Processing. Correct. And let's full screen this. Submit the code. See if we pass all the test cases. Boom. Test case 3. Come on. All right, there we go. All test cases passed. Okay. And so the only problem, HackerRank likes C too much. Yeah. True. Yeah. One of their problems is that they support a bunch of different languages, and so the specific support for C++ isn't necessarily as good as it should be. For example, when we go to the next problem here, go to the next challenge. Not you, maybe the next one. And you're calling the constructor, you'd expect them to have a 2-parameter constructor, one for data, one for next. Nope, they only have a 1-parameter constructor. And it's just super frustrating. And it keeps reminding me to set back to the light theme. Like, no, that's not something I ever want to do. It's really not. Stop reminding me. I really like the dark theme. Okay. So the point here is that, and we can do a couple more of these, so you can kind of see what it looks like. But the point here is that websites like this, or LeetCode, or Code Wars, or whatever, all of them are opportunities for you to just get your hours in, get your practice in. You know, at a certain point, you're going to be sitting at home watching Netflix, and you have to make a decision. Like, you know, do I want to get better at linked lists, or do I want to watch, you know, some Netflix show, you know? And, you know, I don't have an easy answer for you. You know, do you want to play Elden Ring tonight, or do you want to get better at linked lists? And if you had trouble with EU4, you know, you should probably get better at linked lists, because the next one's linked lists also. Just using them, it's actually much easier than EU4. But it's you gotta kind of get on that grind, and you don't have to like kill yourself. You don't have to spend just spend half an hour. If you just spend half an hour a day doing like the easy ones, that just builds your fluency and your confidence. Just do half an hour every day, you know? And if you miss a day, don't beat yourself up, you know? Really don't. Just see if you can figure them out, you know? And one of the nice things is with HackerRank is that, let's exit screen view mode here. I don't know what's going on now. There we go. Is that it actually connects you with employers, right? So the kind of the way they make their money is that all the people that complete the challenges on HackerRank, like, you actually know so and so actually can solve problems in C++. Good on them. And so people who are hiring could be like, yo, give me everybody in the 93731 zip code area, you know, that has a score of 300 or higher by, you know. And so, like, employers, if you turn on your profile, yeah, recruiters can contact me. You'll actually get job offers and things like that for people that are interested in hiring you based on the skills you've demonstrated on HackerRank. So, you know, it's worth, like, just kind of going through the different categories and just, you know, kind of solving them, you know. You know, it's, for me, they're all, like, not all of them, but like a lot of them are like pretty easy. And it's like I kind of got bored kind of going through it, you know. There's a lot of challenges to go through, and I kind of just like, whatever. Register for the Amazon Last Mile Coding Challenge, yeah. So, yeah. So, get a job as a TA like Mincarelli, or go on to HackerRank, stay on that grind, work hard, you know, put up your resume, get hired, you know. Working for a company is a great way of learning, you know. So, Let's go over some of the other options, I guess. There is Hacker War. What is it? Code Wars. All right. Code Wars. Wars.com. Different languages they support. There's C++ there. This code does not execute properly. Try to figure out why. All right. Cool. Solid. You passed the initiation. Okay, whatever. Login. Do I have a login on it? I thought I did. Did I sign in with my GitHub account? I guess I did. Okay. All right. Is your company hiring engineers? Yeah, so same idea, right? Check it out. Check out the job board. And so you can come on here and you can submit your resume and you look for people. And so that's kind of how they make their money. So let's search for a remote OK. All right. Data engineer, senior software developer, Firefly, Java and Angular. Yeah, so yeah, basically that's kind of how these websites make their money, is like kind of putting together employers and people looking for jobs. Oh, look at this. Hazleton has exceeded me in points on. Terrible. So yeah, there is a Clovis Community College team. Let's see here. Let's see, how do we get a link to that? Oh, I'll post the link to it. But all right, and they're each of the tasks have like a difficulty on them, and so what you can do if you're especially like, I know there's a lot of you that like really feel like just like the basics are still kind of like tough for you. What you can do is you can just go like, give me the fundamentals, and here is a challenge to reverse strings. Let's do this. All right, so we click on that. Reversed strings. Complete the solution so it reverses the string passed to it. All right, let's do this. Where is it? Where's the thing? Oh, it's hidden by my face. Okay, there it is. Train. Okay, so it's like HackerRank. So what you have to do is you're given a string and you have to reverse it. Okay. And they got some sample tests down here. Not all of the tests are shown to you. I think HackerRank and maybe Code Wars charges you money to see all of the tests. It's kind of funny to me. Return 1. No, that's not right. You can't return 1. Okay. So how would you reverse a string? Vim mode. Thank you very much. And we'll go to full screen mode. There. Okay. And you can see the input, the output, and undo. Sorry. Okay. How'd you do this? Pay to win on HackerRank. Yeah, really. Yeah. A for loop. Kearney is a great resource. Yeah, I do post jobs on the jobs section. Just got another one or two actually today. I personally think the best way to practice is making projects from scratch with what you currently know without Googling it. Just make something true. But like for like really fundamental things like this, I think like, just think about it, right? Just think about it. So, yeah, maybe a for loop, How would we do this? I will show you how I would do it. Hey, look, using namespace standard. Nice. Okay. Reverse stir.begin to stir.end. That's how I would do it. And then return the string. That's it. Let's attempt this. See if I forgot anything. Sending request. Test passed. Boom. Easy. Standard library. Illegal? Okay, fine. No, that's fair. It's fair. In fact, if I was interviewing at a job and they're like, reverse a string, I'd be like, here you go. Like, no, 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 don't use the standard library. Okay, fine. So there's a couple different ways you can do that. You know, probably the most obvious is doing a for loop. So for int I equals 0, I is less than stir dot size. This is going to be a bug, but I want to demonstrate why it's wrong. And then we'll go stir dot at I, swap stir dot at I with stir dot at stir dot size minus 1 minus I. So when I is 0, it swaps the first letter and the last letter. Stir dot size minus 1 is the last letter in the string. And it's going to swap them. And then it's going to swap all of them, and then when it's the second half, it's going to swap them all back. So this actually needs to be just the first half. So for the first half of the string, we're going to go through and swap each letter with its corresponding one on the back end. And that should be correct, unless I've been off by one error. Nope, all correct. So there you go. And if they don't like the use of swap, then I would write swap by hand. Character C equals this, and this equals this, and this equals this. Be fancy and use recursion. We're going to be talking about stacks today, so why don't we do that one? Include stack. So a stack is a vector with less capabilities. So what we can do is we can make a stack of characters named stack, and we can say for every character in the string, we will say stack dot push that character. So the way a stack works, it's like a stack of plates. So the first thing you push goes on the bottom, the second thing you push goes on the top, third thing you push goes on the top, fourth thing you push goes on the top, then you pop off of it, they come off in reverse order. So it's a way of reversing a string. So we do that, and then we'll stir dot clear, erase the string, and then we will say for let's see, while stack has elements in it, while the stack has elements in it, stir dot push char C is equal to stack dot top, get the top element of the stack, delete the top element of the stack, and then stir dot push back the character. So this is using a, there we go, all of them passed. So it's taking each character from the string, pushing it onto a stack, and then it's going to pop them off in reverse order and add them back to the string. So that's another way you can reverse a string. String has a pushback. Yeah, string is just a vector, really. So pushback exists on strings because strings are really just vectors. They're like a vector of characters with a few extra bells and whistles on them. So, yeah, a lot of different ways of doing it. And the point here is that, let's see. So you can just go to C++ fundamentals and just pick something new and convert Boolean values to strings, yes or no. So if you pass in true, you return yes. If you pass in false, you return no. Oh, okay. How many people here think they could do this? If true is passed in, you return the string yes. And if false is passed in, you return the string no. How many people think you would be able to achieve this feat? Engineering prowess. Next homework summit, all 15 people can work on this together. Why is it not in Vim mode? There, Vim mode. Thank you. There we go. I'm going to do this with the ternary operator. Return value question mark, yes, no. There. Highly advanced coding. I wonder if they don't... Oh, they don't have the string literal suffix on it. Interesting. Try that then. There we go. Yeah. It's interesting. I wonder where that suffix is defined, but either way. So the S, when you do this with an S after the double quote, that makes it a string class string rather than a const char star. So since we're returning a string here, I thought I'd be special and return a string. You know, as it is, returning a const char star is fine because the string class has a constructor that takes a const char star and it will convert for you. It'll do an implicit conversion for you, so it's not a big deal. But I wonder where that's defined. It's interesting. Okay. Emacs is a text editor like Vim. Is it better than Vim? I used to be I used to be an Emacs user. It's a whole other ecosystem to learn. And what's a ternary? This is a ternary. So this is a expression. If statements can't be embedded into like other things, but ternary operators can be. So an expression is anything that can go within parentheses. And so ternary operator is like an if statement expression. And so what it says is that if value is true, then this expression evaluates to yes. That's what the question mark means. If value is true, then it evaluates to yes. The colon means otherwise, evaluate to no. And so it's a little less typing than doing the if blah, blah, blah. Okay. Yeah, okay. So that's my advice to y'all. I would report home for your next assignment, descending order. And so you can choose easy ones like that where it'll just build your confidence. And you pick up points. Like you can see I might have picked up some points on it. You can just sit there and just kind of pick up some easy points. Or you can go for like ranking up, which will give you higher difficulty challenges that will give you more points. And basically the more you do on the website, it's like in martial arts. You start off as a white belt, and then you get your white belt with a stripe, and you level up. So that's why you see these people here at 9th Q, 8th Q is the worst? Okay. 9th Q is usually the worst in martial arts, and you advance towards 1st Q, then you take your black belt test, and then you go into 1st Dan, 2nd Dan, 3rd Dan. So we're all like yellow belts or something, I don't know. Okay. Yeah, that's all I guess I'll say about that. HackerRank, practice your linked list stuff on that. Code Wars, whatever. It's all good. If you join the Columbus Community College team, then you can see the scores of your fellow, classmates and things like that. It's just kind of fun. They have graph theory stuff on HackerRank. Yeah, they got a lot of topics that are all like useful, and highly recommended. Especially if you're just not feeling confident. Turn the difficulty all the way down and just start solving, and it'll build your confidence up. Okay. Extra credit if they practice a certain amount on Code Wars, Lead Code, or HackerRank. I don't know. What do you guys think? Maybe if they complete the linked list section, it'll make up for like EU4 or something. By the end of the semester, give the highest ranked person extra credit. Oh no, that's a race to the bottom right there. What do you think? Like anybody who failed EU4, like just do all the linked list ones on HackerRank or something like that. Seems like an equivalent kind of task. Yeah. Yeah, you can do that then. I'll put something together. Remember, there is a extra credit talk today on Python at 4:30. as soon as class gets out. They'd be nice to do for them. Yeah, I think so too. Especially since the group projects assignment is worth a lot more. And so if you're coming into week 7 here with zeros for both RTX on and for EU4, your grade's going to look pretty sad. So having ability to make that up, it's probably going to be, it'll probably keep some more students in this class. Let's put it that way. And it'll give you the skill you need to get good at linked list. Okay. So, so we're going to talk about 2 new data structures today. Yeah. Stacks I just kind of teased a little bit, but we're going to do queues and stacks. So these are fundamental data structures. They're taught in every data structures class around the world. What kind of separates programmers from like computer scientists is we're going to kind of get into that today a little bit, but you can learn to program without being a computer scientist. How about we put it that way? Computer science does teach programming, but it's more than that. It's the ability to think sort of symbolically and logically and learn kind of high-level conceptual tools and use those high-level conceptual tools to solve problems in a more efficient manner and things like that. And so discrete math and data structures, this class and the next class, CSI 26, those are kind of like the 2 classes that sort of separate out computer scientists from just programmers. And for a lot of job, interview questions, like they ask a lot of questions from discrete math and from data structures. And if you go on HackerRank, you will see a lot of those questions that are actually very similar to the kind of job interview questions people have. Reverse a linked list, and things like that. So it's like the difference between electrician and electrical engineer. Yeah, that's a good way of putting it. Yeah. So are these PowerPoints on Canvas? They are. Go into the Files section, and this is under Qs. I think it's lecture 10 or something. So we're learning 2 new data structures today. And the reason why we're learning 2 in one class and just calling it a day is because, well, you'll see. Okay, so what is a queue? A queue is a data structure in which you put data into it, and then data comes out in the same order. That's a queue. There you go. It's like waiting in line at the bank. So if you go to line at the bank, everyone lines up, and then the teller will call the first person forward. After they're handled, they call the second person forward, and the third person forward. And so the order that you come into the queue is the order you come out of the queue. That's a queue. It's pretty basic, pretty simple to understand. If you implemented a linked list for EU4, basically think of a queue as your linked list where you can push at the front and pop at the back. Right? So you push, things come in one order, push 1, push 2, push 3, pop 1, pop 2, pop 3, and they just come out in the same order they come in. Simple as that. And that's all a queue is. So it's like, you can think of it as like a linked list that has less functionality on it. Okay? Do you have any discrete math textbook recommendations or resources? Yeah, the Zybooks for it is probably the best. I've got a discrete math textbook that I can recommend to you if you want, but it's a door stopper. It's currently holding one of my lamps up. So a queue that's all it is. Like you just add things to the queue, and then when you pop things out of the queue, they come out in the same order. It's called a FIFO, first in, first out data structure. Things come in, things come out in the same order. That's it. And so, yeah, so you can implement a queue very simply. You just make a linked list and you turn off functionality. So you have a linked list and you just allow popping from one end and pushing into the other end. That's a queue. Done. No push front, push back, pop front, pop back. Nope. Push on one side, pop on the other side. That's a queue. There is a data structure in C++ called a queue class, and I never use it because it's just like a linked list, but worse. Less functionality. Yeah, what happened here? Server. Okay. Remove .cc. So do let's do strings. Why not? Invitation. So invitation dot push walker So these are the people on the list that I'm inviting, push, push, push. And then I can say something like this, while invitation.size, while there's things in the list, cout invitation.top, or front rather. And then invitation dot Walker, Michael, Pablo. So I push Walker, push Michael, push Pablo, pop, pop, pop. Front is how you get the first element in the queue, and then you pop to delete the person off the front of the queue. And that's it. That's the whole data structure. That's all it is. So you can add things. It's like push back, I guess. And you can see if there's elements left in it. You can get the first element in the list, and you can delete the first element of the list, and that's the entire data structure. So it's like a linked list with just less functionality. Okay. Priority queues are different. Priority queues are substantially different, but for your average queue, that's about it. Any questions about it? Push, pop, push to add data to it, pop to delete data from it, front to see who's in the front of the queue, size to see how big it is. No insert middle. No. Like I said, it's a linked list with less functionality. Are there any benefits to a queue? I never use it. Right? Yeah, no. I'd probably use a deck instead. A deck is just a queue, but better. You do things like print out all the elements in the queue. That's kind of useful. Like when you're trying to debug things, the ability to just be like, hey, let me look at all the things in the queue right now is kind of a useful thing, and queues can't do that because queues only allow you to look at what's at the front. I think you can actually look at the back as well on a queue for some reason, but you can't actually access the middle of it. And so I just never use them. If I want a queue, I use a deck, double-ended queue, and I just push on one side and pop off the other and call it a day. All right. You can usually use a vector for everything, not for this though. So vectors are terrible at popping off the front. That would be an order n operation, whereas for deck it's order 1. Right, so why won't they get rid of these less useful data structures? Well, so that was the same question asked in the previous class. And the non-cynical answer is, well, what if you want to guarantee that you can't, like with the deck, I can't guarantee that you won't push on the front. You know what I mean? Like I can't guarantee it. With the queue, you can guarantee the only place you can ever add to the queue is at the back. And the only place you can ever delete from it is off the front. That's guaranteed because it's a queue class. It's got a contract that can guarantee that everything is FIFO. Whereas with a deck, it's up to the programmer to make sure they don't do a push front instead of a push back, and to do a pop front instead of a pop back. So the non-cynical answer is if you use the queue class, it can guarantee the FIFO-ness, first in, first out-ness of it. It's never been an issue for me though. Like if I needed to act like a queue, I just have it act like a queue. And then when I want to see what's in the queue, I can just print it, The slightly more cynical answer is that they added the queue class and the stat class and the forward list class simply because this class, because of CSI 41, because of the data structures. Because every data structure class around the world teaches linked lists, queues, and stacks. And despite the standard library having better options, I feel there's probably some political pressure from somebody who's like, look, we need to have these things in the library because everyone's like, where is the Q class? Where is the stat class? Where is the singly linked list class? And so I think they just added it for completeness sake, is my cynical view on it. Just stop bothering me. Stop asking me where the singly linked... Here you go. It's called forward list. There you go. It's done. But I literally never use them. Unironically. Right? Like if I'm making a homework assignment or something, I might make one. Or if I'm demoing code like this, I might use the Q class. But like when I'm actually writing code, no. Never. They're pointless. Okay. Bjarni loves his Qs. Actually, from what I understand, like Bjarni challenged the committee, like give me an example of a problem that needs singly linked lists. You know, and I don't think anyone actually answered his challenge. Like, you know. So, Q.back is the thing. Yeah, you can print the last element of a Q for some reason. Even though it kind of doesn't make sense. No, I don't know. Okay, so there we go. That's Qs. Let's, if you want to think of it conceptually, it's like waiting in line at the movie theater. Person 1 gets added to the queue. Person 2 gets added to the queue behind them. Person 3 gets added to the queue behind them. The teller calls forward person 1. Person 1 pops off the queue. Person 4 comes in at the end. Teller calls forward person 2. Person 3 comes forward. Person 4 comes forward. It's all pretty straightforward. Pushes and pops. Okay. So the way that queues can be implemented, you can actually implement queues a lot of different ways. A lot of years I actually have a queue assignment where you have to like write a queue using linked lists or decks or vectors or circular arrays and time it to see which one is faster. We're not going to do it this year. We got a lot going on. So a circular array though is kind of a neat idea. It's sometimes called like a ring buffer. And what the notion is that if you call push 1, push 2, push 3, push 4, push 5, push 6, you've just got two integers. You have an array of size, what is this, size 8 here? So this is a size 8 buffer. And you've got like head here. So head is equal to 0, and you got tail 0, 1, 2, 3, 4, 5. So you got tail. It's just an integer, it's not even a pointer. And tail is equal to 5, index 5. And then if you call push, like push 7, then what happens is you write 7 into the next available spot, and tail is now 6. Okay. And then if you call pop, what happens is you delete that, and then head becomes equal to 1. So head's now pointing here. Call pop again, that gets deleted. Head advances 1 as well. Head's now 2. And you can insert 8, insert 9, insert 10, pop, 3 comes out, pop, 4 comes out, insert 11, insert 12, insert up, crash, out of room. Okay? So the way that this works is that if the index ever crosses over 8, then you do modulus. And so basically you increment the index every time you push or pop, whether it's the head or the tail, whichever one it is you're moving, it always goes up by 1, and you use modulus to wrap around n as the size of the array. So you would say something like this, like tail plus plus, and then tail is equal to tail modulus 8. So every time you push, tail increases by 1, index 4, index 5, index 6, index 7, index 0. Index 1, index 2. And so it'll just keep going around in a circle. Now, these things are called circular arrays. In RAM, though, they're just a regular array. What happens is that when you go off the edge of one array, you come back in on the other side. And so you use the power of modulus for that. And it allows you to have a little buffer. So one of the main uses of a queue is when you have producers and consumers that are out of sync with each other. So think about, have you guys ever had a situation where like you're typing on Microsoft Word and like Word kind of like freezes for a second, and like the screen goes gray, and it's like waiting for Word to respond, but you're like still typing. So what happens is that when you're typing, you're producing data, right? You're producing data, you're producing keystrokes. And those keystrokes are all going into a buffer. Your operating system has a buffer of a certain size. It's a circular array, almost certainly. And all those keystrokes go into that buffer. And when Word is ready, it'll consume the keystrokes out of that buffer. And so what you'll see is like once Word starts responding again, all those letters go, and they appear on the screen. And because the buffer has a limited size, you can actually fill it up if you type too much and it freezes for too long. But for like normal circumstances, you can actually type several words ahead, and then the words will suddenly appear on the screen. Same thing if you're like on the server and like the server lags out or something. You can keep typing, all of that goes into a queue somewhere. And so you're producing data, and Vim or Word or whoever is consuming the data, but they're not directly in sync with each other. And so anytime you have a circumstance where the producers of data and the consumers of data are not one-to-one in sync, you usually have a queue. There's usually a queue somewhere in between there that buffers the data between them. So for example, if I were to fire up Pokemon Go, I did this in the earlier class, and okay, there you go. So if you see Pokemon Go here, there is no Pokemon anywhere near me. And so what's happening right now is my app is probably connecting to the Pokemon Go server. And the Pokemon Go server is probably starting to send data to me. It's probably trying to transmit to me all of the Pokemon that are in a 10-meter radius around my person here. Now, what's going to happen is you will see absolutely nothing on the screen until all of a sudden all of it appears on the screen. And what happened was the server was transmitting data, but because there was no connection, the connection was still being established. Kearney survived Blood Moon. The server is transmitting things, but my app is not receiving it yet until it negotiates like the handshake with the server or whatever. And so once it gets all set up, then I start reading out of the queue, and all the things appear, and they appear in the same order that the server sent them to me. And that's actually really, really important when you're working with network applications, is that if you say, hello, my name is Bill, that the words arrive in that same order. Hello, my name is Bill. And so when you transmit these packets, hello, my name is Bill, they go into an outgoing queue. And then when the other person's ready, they're like, send me data. And you'll send them data. And then they're like, whoa, stop sending me data. I'm congested. And then it'll stop. And then, okay, send me data again. Okay, and then it'll start transmitting again. And you have what's called a window or a transmit buffer or whatever you want to call it. And that's basically a queue. So anytime you have networking applications, there's going to be queues in there somewhere. Okay. Anytime like data is being produced and consumed, there's usually a queue that kind of handles the differences in data production and consumption. Okay, you guys understand that? This happens with your clock machine at work. I'll push a number and sometimes it freezes. World's slowest machine. Is that how a string stream works? A string stream, you can dump things into a string stream and you can call it a queue, I guess. Yeah, you can see out into it. And then when you read out of it, yeah, sure. Aren't vectors circular like lists in Python? Because a vector is a contiguous block of RAM. That's all it is. If you want to turn a vector circular like this, you can just add on to it by doing a modulus. So that's queues. They're not really very complicated. Can you explain the modulus part? Yeah, so for a circular array, every time you push or pop from a circular array, either the head's going to move forward one or the tail's going to move forward one, right? So if you pop, right now the index is 0 here. Oops. So head is currently equal to 0. And if we pop, head moves to 1. If we pop, head moves to 2. If we pop, head moves to 3. We pop, head moves to 4. We pop, head moves to 5. Pop, head moves to 6. Pop, head moves to 7. pop, head moves not to 8, it moves back to 0 again. So every time the head advances, you do a head plus plus, you say head is equal to head modulus the size. In this case, 8. Or you can use size. Okay. And then that wraps the head back around to 0. And you do the same for tail. Every time you push, tail increases by 1, and you modulus it by size. And what this allows you to do is allows you to push, 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 pop, 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 push, 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 pop, 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 push, 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 pop, pop, pop. And the head and the tail will just keep chasing each other around the circular array forever. If you ever pop too many, then it'll segfault or something. I don't know. Throw an exception probably. And if you run out of room in the buffer, if you push too many times, it'll run out of room. It'll probably also throw an exception saying you're out of room. Okay. All right. See more. Yeah. So rather than like index 10, if you do 10 modulus 8, that turns into 2. Right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Instead of 10, this is 0, 1, 2. So modulus is inherently linked with circles. If you want to think about like how a clock works, when you go past 12, it turns into 1 again, right? So you keep adding 1, you keep adding 1, you keep adding 1, and you modulus it every time, right? Keep adding 1, keep adding 1, keep adding 1, and you keep modulusing it by n. And then if you ever exceed the maximum, it wraps around to the minimum. Okay, so that's a Q. Let's talk about stacks. So rather than a queue, let's do a stack. And for a stack, stacks use top instead of front because stacks are viewed vertically, mentally speaking. So for a stack, if you push Walker, push Michael, push Pablo, it's like putting plates on a table. Walker goes on the bottom, Michael goes on top, Pablo goes on top, and then when you pop off a stack, Pablo comes off first, then Michael, then Walker. And so stack is like a queue, but kind of backwards. So you can see it went Walker, Michael, Pablo with a queue. That's the order they came in. With a stack, Pablo comes off first, then Michael, then Walker. So stackwards. Okay, so yeah, basically a stack is kind of like the opposite of a queue. Queues are first in, first out. The first element you add is the first element that comes out. A stack is last in, first out. So the last thing you put into the data structure is the first thing that comes out of it. So over here we can see Pablo was the last person we added to the stack. So Pablo was the first to come off the stack. Conceptually, pretty straightforward. Have you guys ever encountered that situation with your fridge where like you put things into your fridge and like the new food goes in front of the old food, and then when you want to eat, you eat the new food, and the food in the back like just kind of sits there and like kind of gets sketchy after a while? Do you ever use stacks? I'll show you. No, but I'll show you. They're useful, but I don't use the actual stack class. You know what I'm talking about? Like with the fridge, like, you know, you got your yogurt at the front, you're like, oh, that's fresh, I'll eat that. And then in the back, there's the yogurt that's been there since the 1990s, you know. First in, first out, FIFO's food service acronym. Yeah. So have you ever seen a fridge at a grocery store? Like the dairy aisle? Do you know how the dairy fridges work at a grocery store? Have you ever seen these? You ever pay attention to that? Neglected yogurt, yeah. I once lived in a house that was so bad that a person had left a potato in there for so long, the potato had actually sprouted, and we actually had a stalk growing up through the through the racks, and there was this leaf in there that was like, "Love me," and yeah, it was disgusting. Used to refer how groceries run accounting and inventory, right? So for places that don't have like grocery store fridges, they'll actually do a stock rotation every once in a while, where they go in and they do a reverse. You know, where the oldest things in the back get reversed to the front, so that when people buy them, they get the older stuff instead of the newer stuff. Can't get potatoes get poisonous or something? I don't know, man. I was not eating that. Like, I was not eating that potato. Like, I was just like, I'm not. No. that was one of the worst places I ever lived. I was living in the living room. Like, I didn't even have a bedroom. I had my bed in the living room next to the pool table. But they don't. Yeah, perfect. Yeah, when I worked at a grocery store, we had to move the food from the back to the front. Basically, had to use the STL. Yeah, it's like a reverse algorithm, right? Now, at a grocery, though, for the dairy aisle, they actually load the dairy from the back usually. So if you're ever in there and you see people putting milk in, they actually put milk at the back. And so when people buy milk, they take it off the front, and then the new milk comes in the back, and so that's a queue. So the fridge at a grocery store in the dairy aisle is usually a queue. The first one to come in is the first one to come out. Whereas in your fridge at home, it's usually a stack, right? The oldest stuff is in the back, and the newest stuff's in the front, and yeah. First in, last out. Yeah, FOMO. Okay. Potatoes are a member of the nightshade family. Okay. So yeah, you push 1, push 2, push 3, pop, 3 comes off. And we think of it conceptually as being the top of the stack. That's why it's the top of the stack, but the front of a queue. We use different words for essentially the same thing. So push 1, push 2, push 3. 3's on the top, so when we call pop, 3 comes off. Push, 4 goes on the top. Pop, 4 comes off. Pop, 2 comes off. Pop, 1 comes off. Any questions about this? Conceptually, I don't think queues and stacks are conceptually very hard to get at all. Push, push, push. Pop, pop, pop. It comes off backwards. 1, 2, 3 gets pushed on. 3, 2, 1 gets pushed off, popped off. Stack, shoving people in the room and taking that close to the exit. Queue, line of the movies. Yeah. Yep. Okay. So a vector is actually a stack. So you were asking me earlier, do you use the stack class? And the answer is nah. Same issue. Same issue as before. In fact, the standard library stack class isn't actually a real class. It's not a real class. It's something called an adapter class, where they just take an existing class and then they turn off features. So the queue class, and the stack class are actually just other containers that they've disabled features on. It's like what were we talking about earlier, Mincarelli? Like Rainbow Six Siege, when you get like the free-to-play version, you don't have all the features turned on. It's like that. Let's see here. So rather than using a stack class, I use a vector. Because vectors you can push and pop at the end. Right? So you push back, push back, push back, pop back, pop back, pop back. It's a stack. But it's a stack that you can actually like say, hey, print out everybody in the stack. Right? Which is something I usually want. When I'm debugging, I want to be able to see, hey, what's in my stack? And the stack class doesn't allow that. The stack class only allows you to push and pop off the top and see what the top element is. And that's it. And size. That's it. That's all you have on a stack class. And so they're just like vectors, but worse. They're vectors. They're literally vectors with less functionality. And again, the non-cynical view is you use one if you want to guarantee that the stack property will never be violated, right? Like that you will only ever change something on the top of the stack. Whereas a vector, you could always be like, Walker is now uninvited, right? Like I could feasibly delete his name from existence, right? Whereas with the stack, that's not allowed. And so if you use the stack class, it's going to sort of guarantee the stack property is not violated ever. But I don't use it, ever. Queues and stacks and forward lists never use, ever. A stack is a lobotomized vector. That's exactly right. And in fact, if you look at the source code for it, that's literally all it is. All the stack class is it's not even its own class. It's just another class with functions turned off on it. So a vector is a stack on crack. A vector is a real class. Stack isn't even like really a real class. Okay. So yeah, instead of using a stack, use vector. Instead of using a queue, use dec. It's my advice. Instead of using a forward list, use a list. That's kind of my advice. I'm sure there are purists out there that have opinions, and I don't really care about that. Okay. Yeah, so that's stack, that's queue. They're very fundamental concepts. Like, these are very fundamental things in data structures. It's just like, and they're useful. They're used a lot. Right? So, for example, the stack is used in the stack. If you've ever heard about stack allocated and heap allocated variables before, well, so stack allocated variables are up here, and every time, here you go. I guess that'll work. Okay, so every time you call a function, the stack moves downwards, and it makes enough room. Usually ints are 4 bytes each, right? So it makes enough room for all the local variables like x and y and z. And then if the function calls another function, the stack moves down some more and makes enough room for their variables. And if that calls another function, the stack pointer moves down some more. And every time it moves down, it moves down far enough to hold all of the local variables in that function. And then when it returns, the stack goes back up. And so it's literally a stack. Like, a function calls a function, calls a function, returns, calls another function, calls a function, returns, calls a function, calls a function. And so the stack is really good at very quickly allocating variables, allocating memory for variables, and deallocating memory for variables. Let's see if we have a good picture on here somewhere. This one. No, it's making a stack. Yeah, it's a stack. And these pictures are particularly persuasive. So yeah, stack pointer moves down every time you call a function, and it rewinds back up when a function returns. So it's a stack. It's just a downwards facing stack. It's a stack that grows downwards instead of upwards, like we normally think of it. Okay, so reversing a word, I showed you the code for that earlier, right? You push hello onto if you push hello, the string hello, H-E-L-L-O, onto a stack one character at a time, H-E-L-L-O. When you pop it off, you get O-L-L-E-H. Simple way of reversing something. Parentheses, if you're doing like algebra, like if you're parsing algebra, every time you get an open parentheses, you push it onto the stack. Every time you get a closed parentheses, you pop off the stack until you get to the open parentheses. That's how you do parentheses matching and things like that. So you can check, because if all you did was count how many open parentheses and closed parentheses there are, this would be fine, right? Because there's one closed and one open. But with a stack, you push onto the stack, 1 plus 2. When you get the closed parentheses, you pop off the stack, 2 plus 1 here, and you evaluate that to be 3. And then when you get this closed parentheses, you evaluate the 3 divided by 3 to be 1. And you pop. So that's, algebra is typically done using a stack as well. Writing a calculator, yeah, that's there's actually these things called stack-based programming languages where you push things onto a stack and pop things off a stack. And RPL, if you've ever used like an RPL calculator, you push values onto the stack and then pop things off the stack. But that's really about it. Like that's basically stacks and queues. They're conceptually like pretty easy, but they do come up a lot, like in practice. Like use a stack to track the algebra or something. Conceptually though, not bad. Okay, so one last thing. We got 15 minutes left. Let's talk about Big O. So Big O is can be thought of as the as a problem gets bigger, how does the running time change? Let's put it that way. So for big O, you've heard me using the term a lot. I'm actually going to get into it a little bit now. So big O is basically this question. Okay. So if you're going to graph, that n is the size of the problem. Like, let's say you have a vector, and the vector is of size 100. N is 100. If the vector is of size 1,000,000, n is 1,000,000. Okay. It's the size of the problem. How does the running time change as the vector gets bigger? So like, for example, if I was just printing out all the elements in a vector, I would expect this to be a linear relationship, right? We call that order n, or a linear relationship. So in other words, if there's 1,000,000 people in the vector, and it takes, I don't know, a minute to print, I would expect that if I have 2,000,000 people in the vector, it'll take 2 minutes to print. And if I have 3,000,000 people in the vector, it'll take 3 minutes to print. If I have 4,000,000 in the vector, it should take about 4,000,000 to print. Obviously not exact. None of the stuff we talk about here with big O is exact. Like, they're all just kind of like big spitball estimates of, mostly what we care about is the shape of this. Like, as the vector gets bigger, what is the relationship between the size of the vector and the running time? And if it's roughly linear, then we call that order n. Okay. So something faster than order n would be considered like one of these things, which is order log n. And so this would be a logarithmic algorithm. So for example, if you have a sorted vector, like a phone book, right? And you want to find a name in a phone book, you don't start at the beginning and read to the end, right? Unless you're just like, you just like wasting your time. If you have a phone book, what you do is you open it up halfway, right? And you're like, all right, I'm looking for OTOL. All right. And I open up halfway. Okay, O is to the right. Okay, so you can kind of conceptually rip out half of the phone book and throw it away and repeat. Open it halfway. O is to the left. Rip out half the phone book, throw it away. If you have 1,000,000 names in a phone book, you can find any name in the phone book in 20 steps or less. Log base 2 of 1,000,000 is about 20. Okay? And so that's much faster than linear, right? A linear search would be, you start in the A section, you're like, all right, OTOL. You know, and you just go from the beginning to the end. Worst case for that is you go through all 1,000,000 names and then you don't find it. You know? So if you could linear search a phone book, but it's stupid. It's sorted. And if you have a sorted phone book, then you can jump halfway and then jump halfway and then jump halfway and jump halfway. And whenever you have an algorithm like that, it's going to be logarithmic in nature. Logarithmic is very, very fast. A lot of people don't understand what a logarithm is. A logarithm is the opposite of exponentiation. So imagine the opposite of this, order 2 to the n. This would be an algorithm where, like, let's say that you're trying to figure out the fastest route from, here to Fresno State. And you try every combination of street, right, from here to Fresno State to see which one's fastest. That might be like an order 2 to the n algorithm, trying every combination of things. And or if you're trying to evaluate truth tables, right? If you have n binary variables, there are 2 to the n possibilities for their values, right? Like, if you have x, there's 2 possibilities, 0 and 1. If you have x and y, there's 4 possibilities. There's z, there's 8, right? Every time you add a new variable, the number of possible combinations doubles. Right, and that's one of the reasons why it's hard to verify truth tables for large numbers of input booleans, because every additional boolean you add doubles the amount of work you have to do. This is really bad. Like, for 2 to the n, you can solve a 2 to the n algorithm for like 5 or 10 or something like that maybe. But think about how big a number 2 to the 100th is. Like, even for like 100 cities or 100 streets or 100 boolean variables, it's going to be too big for even the world's most mightiest supercomputers to handle. So this is like, this is bad, right? This is what we call intractable or unsolvable. And even worse than order to the n is like order n factorial, right? An example of that would be try every possible shuffle of a deck of cards and see what percentage of them, have 3, 4, and 5 in a row in them. Generate every possible shuffle of a deck of cards and count how many of them have 3, 4, and 5 in a row somewhere within them. And that's really bad. Order, and this is like, these are both like just, they're so bad, you can solve them only for very small toy problems. Beyond that, it's just intractable. Heat death of the universe kind of stuff. And this is what really separates computer scientists from programmers, right? Is this notion of like algorithm analysis and kind of understanding the math. It's not really math exactly, but kind of just understanding the relationship between the size of the problem. This is size, right? And the time that it takes. And none of these things are like super precise, like, like if you're counting a million elements, like every time you count something, it might be like 3 operations to count it or something. Like if you're iterating across a linked list, right? Like, you print out the value, then you set the pointer to the next, and then print out the value and do a check. And so you might be like, well, that's 3 million operations, not a million. Yeah, we don't care. We don't care. When we're talking about order big O, what we're really interested in is, as the problem gets bigger, what is the shape of this curve? What is the shape of that curve? And for just like printing out all the elements in a linked list, it's order n. Like just the time goes up linearly. The more elements you have, the more time it takes, and it's just proportional. It's an order n. It's a linear relationship. Now, a common one you'll see in here is this one, and that's order n squared. And that's called a quadratic, right? And so if I were to, if I had 1 million elements, it would do roughly 1 million squared operations. That's way worse than 1 million. It's 1 million times worse, in fact, right? And 1 million's not even that many, operations. You know what I mean? So again, we don't care if it's 999,999 squared or 1 million squared. Like, this is all very high-level approximation kind of stuff. Okay, but you really want to know, like, is my code order n squared or order n? That makes a huge, tremendous difference in running time, right? Even if you have like 100 elements, it'll be 100 times faster to do linear than quadratic, right? 100 times faster, and that's for 100. That's not even a large number, right? So let's give an example of that. So, and of course you have n cubed and n fourth and things like that. But these are there's one that we forgot before I give you a code example, and that is of constant running time. Constant running time is very important. Order 1. So for example, if you push at the front of a linked list, basically you knew something, you hook up the pointers, move head up. It does not matter how big your linked list is, right? You could have 1 billion people in the linked list, and pushing at the front of a linked list is still order 1 time. Constant running time. It doesn't mean it's one operation. We'll sometimes say... Aaron, can you mute yourself? But what it means is that it... Thank you. What it means is that it always takes the same amount of time. If the linked list has 5 people in it, 1 million people in it, 1 billion people in it, it doesn't matter if it's order 1. It just always takes the same amount of time. Okay? So let me show you some code and how this kind of makes a difference. So this loop here is what we call order n cubed. So if I type in 1, it prints out 1 high. If I type in 2, it prints out 8. If I type in 3, it prints out 27. So the reason why I knew that this was order n cubed, though, is because I could look at the for loops. Usually when you do algorithmic analysis, you're going to be looking at the for loops. That's the important thing. And so if you just have a single for loop like this, I think everybody here can see this is going to run n times. So if n is 10, it runs 10 times. It's going to print high 10 times. If you have two loops like this, then 10 times, if n is 10, 10 times it'll print, it'll see out high 10 times. So it will do 10 times 10 n squared operations. And if you have triply nested for loops, then it's n cubed. And so this way of just kind of like looking at a linked list and just being like, all right, this is a triply nested for loop. Each one of them is going up to n. That is n times. It will do n work. And each one of those, it'll do n work. So that is n times n times n. The cout statement there is going to run n cubed times. And that's kind of the high level, easy does it way of looking at an algorithm to see how fast it runs. Now there could be tricky bits. Okay. So what if instead we did this vector? Flip. Okay. There we go. Vector of ints named vec of size n. All of them initialized to 42. So if we have 10 elements of size 42, this itself is an order n algorithm because it's going to create 42 copies of n. So if you tell it to make 1,000,000 42s, it will do roughly 1,000,000 operations on it. Okay. But here's the thing. So let's do this. Vec.erase, vec.begin. So if we have 1,000,000 elements, 1,000,000 times we will erase the first element out of the vector. What is the running time of this? This loop will run n times, right? But what is this running time? Yeah, every time you erase from the start of the vector, it has to shift all the remaining n elements forward by 1. And so vector.erase is not an order 1 operation, it is an order n operation. Yep. And so n times it'll do n work, and this will be an n squared algorithm overall. Yep. And that's why it's important to pick the right data structure for the job. If instead of using a vector, I decided to use a dec, pop front on a dec is constant running time. And so by switching from a vector to a dec, I was able to decrease the running time of this algorithm from order n squared to order n. And that's why data structures is such an important class. If you pick the right data structure for the job, even for smaller sizes like 100, this code will run 100 times faster. For 1,000, it'll run 1,000 times faster. For size 1,000,000, which isn't even that big, it'll run 1,000,000 times faster. It's always important to pick the right data structure for the job. And that's why we mandate every computer scientist takes CSci 41. Thank you for coming to my TED Talk. Any questions? We got an extra credit talk coming up in 1 minute, so show us order n. Order n factorial. Yeah, the example I gave you is basically generate every possible shuffle of a deck of cards. And that's order in factorial. Sorry. Yeah. So, okay. So Aaron is unmuting himself again. He's getting ready. Yeah. So anything that's order exponential or order factorial, this is the bad kids club. Bad. This is yeah. This is the good kids club over here. Yeah, you can start on linked list stuff before I create the assignment for it. All right, so that's it, and I will turn it over to Aaron in 1 second. Let me just save the recording. All right, see you guys Monday.